15 is E. 16 is also E. 18. C. 18 is C. 20. E. 21. E. 22. Oh. 22 is E. E. We might want to go over that one, says it. 24. C. 25. 25 is C. That was C. Did I say that was C? 30 is C.
30 C. Cool.
Remember, 65% is an A. 34. 34. B. 34 is B. 35.
Question.
Yeah, that was a Was it A?
That one is A.
Yay.
That one is A. 39. E.
Yeah.
E. 42.
E.
E.
I was pretty confident.
Or we just guessed it.
I think
Oh, this is what
E.
C.
Oh no.
C. 43.
A. I also had A.
A.
Dang it.
44.
E. C.
44 is C.
Nice.
Y for redemption.
And 45. 45 is E.
Yeah. A.
What if I was
E? Which one? Oh.
45 is E.
What was 44?
What was 44? C.
Oh, okay. Then I was
44 was C. Okay. So there was one here early.
Wait, are we not going to this stuff?
22.
Those look like this class thing. I started question marking on the one how to put the answer.
smart?
No, I didn't get it right. I don't know.
This one, 22.
The answer is C though, but I don't know why. No, I don't know.
So 22 was one of them, right?
Yeah.
Where we had a fair number. All right, so they tell us this. Now it seems maybe one of the classes did this and one didn't before Christmas. For some reason this one looks. But then so many of you have switched classes now. You know what I mean? So what does this mean? Y double prime, right? Second derivative. That's just Leibniz notation for second derivative. So what they told us is y prime is x squared y squared. So how do we do y double prime? Do the derivative again. So the derivative of y prime is y double prime, and then we have to do a product rule on this. So it would be 2x. Do we tack on next prime? Because this is not with respect to t like a related rate problem, right? This is with respect to x, right? So x prime would just be 1, dx, right? So no. So 2x, leave the y squared alone, plus x squared left alone times 2y y prime, right? 2y y prime. Now, if you forgot the y prime, you would have ended up with 2x y squared plus 2x squared y which is D, right? See, so that's what we were talking about. Just kind of one of those common mistakes. And it's there, and of course, when you see your answer that you're there, you're confident, right? So, I mean, and it doesn't always happen that way, but that is the case here. All right, so how do we, and we look at that, and none of those are there. So what do we do? Yeah, we know what y prime is. It's x squared y squared. So we just substitute it in. So we got 2xy squared plus 2x squared y with a x squared y squared plugged in there. So now it becomes 2xy squared plus, and then this would be 2x to the fourth y to the third, which is choice E. And that always is going to happen on implicit differentiation when you do the second derivative, because you're starting with a y prime, you're doing the derivative of that. Well, that derivative probably has y's in it, so you're going to be sticking in a y prime somewhere. Your y double prime is going to have some y primes in it, but you couldn't have got to the y double prime without first having y prime. So wherever a y prime ends up showing up over here, you'll just substitute that y prime in, and then you'll have it. So it would happen that way every time in implicit differentiation you do the second derivative. Every time. Okay? What was next? 25, wasn't that one that seemed like there was a lot of... Okay. When does when x gets really big, when does a fraction go to 0? Well, yeah, you could say a constant over infinity. It also could be infinity over infinity when, what has to happen for a fraction to go to 0? The bottom has to get way bigger than the top. The bottom has to get way bigger than the top. That's what has to happen. Okay? So the G has to get a lot bigger than the F. So would x squared get bigger than e to the x? No, it's the other way around. Exponentials get bigger. Okay? ln x, does it get bigger faster than that? No, ln x goes like that. It doesn't get big very fast at all. What about this one? Yeah. That's the one, right? E to the x is going to get a lot bigger than natural log. And again, on this one, ln x levels off where x goes like that. So ln x is slower. And then here, 2 to the x gets really big, really fast, but 3 to the x gets bigger faster. It's got a higher base, right? So they're both getting really big, but the top would be getting bigger faster. So the only one where the bottom, the G, is getting bigger faster is C. That's it. That's what that was about. So just, again, these packets do a good job, and I think the test does a good job of approaching these problems in ways we haven't quite seen to really see if you understand what's going on, right? And I think the process of practicing and reviewing for these, and that's why I love the packets, and you guys hate the packets, but, or will hate them if you don't already. But, but honestly, they are one of the best things we do all year long for your long-term, remembering, I think, of what to do. So when it comes to next year and you have to take calc again and so forth, because it just forces you to go back and rethink of these things without just memorizing, do this, do this, do this. There's some of that for sure, but it really makes you think about the problems in different ways and the concepts in different ways. Okay, but we're just starting this process, so it's harder now than it will be eventually. The midterm's always a little harder, I think, from the standpoint it's the first time you've taken the tests of that difficulty and you haven't spent a lot of time in the packet. And then when we get to the end of the year, the test, you're more familiar with the problem, so that makes it easier. But then there's a lot more stuff, right? By the time we get to the end of the year, now you're gonna be going back and reviewing all this derivative stuff and limit stuff that you haven't done for a long time, right? That's the hard part about at the end of the year when we review, is going back and remembering this older stuff. Okay, so for us now, it hasn't been as long since we did this, so that part's not as hard. Okay, moving on. Now we get into the calculator section probably. And I know you wanted to go like 42 in those. Were there any before that? I can't remember. 30 what? 5? Oh yeah. Yeah, we can do that one for sure.
What about 34?
About 34, let's look at that one, sure. Okay. Alright, so let f and g be differentiable, which just means their derivatives exist. That's all that means. And we got all this information here. So if h is this, okay, then what's h prime of 1? Well, remember, I used to say this a lot. Before you can find h prime of 1, you have to find h prime of x, right? And then you plug a 1 in. Well, if this is h of x, how do you do h prime of x? Well, it'd be what? Derivative of this. What's the derivative of that? F prime. Leave the inside alone. Times g prime of x. Just chain it, right? Just chain it. Derivative of the outside, which is f prime. Leave the inside alone, g of x, times the derivative of the inside. So h prime of 1, let's just put a 1 everywhere. So what's g of 1? 3. So now that's f prime of 3 times g prime of 1. Now maybe that was the difficulty. Probably the difficulty was not getting the derivative, right? So once you have that, then it's probably pretty easy, okay? But now we just plug those in. So f prime of 3 is negative 5, and g prime of 1 is negative 3. Right? So which is 15? B. See, to me, that's one. That's one that I would be expecting to see work, right? Because this is a calculator problem. How useful was your calculator then? Not useful at all, right? Now, I think the calculator, you could type this in as functions and do the derivative. It would look really weird. It wouldn't use prime notation. It would use Leibniz notation. If you, I always say if you have to use your calculator to do the derivative of this, you got a lot more problems than whether you can get this answer right. You know what I mean? I mean, it's not going to be good if you've got to use a calculator. So when I look at the calculator in this one, the calculator is really no use. And they do that. And again, the calculator section just means if you need it, you can use the calculator, right? Some of the problems are specifically written in there that the calculator is really not going to help, okay, unless you needed it to multiply those two numbers right there, okay? But again, probably not, okay? So, you better be writing something down, right? Write some stuff, have stuff written down. If you just have a B in there when I go and grade these, that's not that good because I told you that. All right, let's look at this one. So the figure above shows a road running the shape of a parabola from point A to point B. So it's a parabola until here, and then it's a line. The equation is this, so it's a piecewise function. B is 1,000 feet horizontally from A and 100 feet higher. So what they didn't put on here, which would be good to put on, which is 100 right there. Since the road is smooth, R prime is continuous. What that means is R prime exists, right? Because to be continuous, a function has to exist, the limit has to exist, and the function and the limit have to be the same. Okay? In other words, what they're saying is this slope is changing, and then right there, the slope of the parabola is the same as the slope of the line. That's what it means by smooth. That's not a sharp point. Sometimes, if you have a parabola that turns into a line, there's a sharp point there, which means the derivative doesn't exist, which means the slope coming in is different than the slope going out. That's what creates a sharp point, not smooth. Smooth means the slope coming in is the same as the slope going out, and that really is the key to this problem, okay? Because that means that the derivative of this, which would be what? 2ax is going to be equal to the derivative of that, which is b. Without that, you really can't do this problem. That's the key to that. Since the road is smooth, the derivative... Now, we did this a lot with these piecewise functions, right? If this graph's going to stop somewhere, and then the new graph's going to start in the same place, what do you do in that case? Which is what we have here also. You set these two equal to each other, right? So we need that as well. So this parabola stops here at 1,000, and then the line takes off also at that point. So we also know that ax squared is going to equal bx plus c. So we got both parts of that. To be continuous, a piecewise function has to connect, right? There can't be this gap there. So to be continuous, these two have to be equal at the point where they separate, right? At the point where they switch. But to be smooth, it has to be more than that. To be differentiable, it has to be more than just continuous. It has to not only connect, but it can't have a sharp point. So their slopes have to be the same. So the derivative of each of those has to be equal. Okay, well, what do we know? We know at this point, we know x is what? 1,000. So we know that we're going to put 1,000 in here. So we got a and then 1,000 squared. That'd be how many? 6 zeros? Right? And then 1,000b plus c. Now, I'm not sure I actually need to set those equal to each other just yet, because I also know this has to equal what? What does ax squared and bx plus c have to equal at 1,000? Doesn't it have to equal 100? They have the same y value, right? So the parabola, so I could do that right here. Right here, I could just take 1,000,000 times a, and that's got to equal 100. Right? So I actually didn't have to put these two together. Because when I look at that, I think, well, that's not all that helpful because I got 3 variables in there. But I know more. I don't even know, I don't even have to talk about it being equal. I just want to find what a is. So I know it's got to equal 100. So I divide that. 100 divided by that, what's that going to be? 1 over 10,000? Right? Of course, you got your calculator to help you with this a little bit. So 100 divided by 1,000,000 would be 1 over 10,000. A couple zeros would cancel out. And now I can come put that in here. So I got 2, and aren't they trying to find the value of b? Yeah, so now I've got those two are equal. So now I know what a is. A is 1 over 10,000. And what was x? X was 1,000. Right? At the point in question. Right? At the point in question where their slopes have to be equal, right? Their slopes have to be equal. Their slopes aren't equal anywhere else except at this point, right? So their slopes are equal when x is 1,000, and we just found out that a is 10,000, okay? So now what do we got? 3 of those, cancel 3 of those, and I got 2/10, 0.2, which is a, okay? So there's a little extra arithmetic in there with all this stuff, and the numbers got kind of big, but you had a calculator there. But that was the key. So I didn't really need to set the two equal to each other. I really only needed the parabola since they told me the 100. That was kind of the key. They told me the 100 there, and that was helpful. Okay? All right. Now let's go to, now we get into like 42. And those, was that kind of what was next? All right, so 42, the amount of a product is given by A, so that's the amount, T is the number of hours. What time is the rate of production increasing most rapidly? So the most common mistake here is people do A prime and set it equal to 0. How many people did A prime and set it equal to 0? Don't be afraid, raise your hand, okay, because, okay. And those of you that didn't raise your hand, what do we want to do? A double prime. Okay, let's think about it. When is the rate increasing most rapidly? So it sounds like there are 2 ways to handle this problem. One is as a max, because we've been doing maxes a lot right now, so that's probably in your head. When is the rate increasing most rapidly? Well, what do they want the max of there? And the rate would be A prime. Right? The rate is A prime. And they want the max of A prime. Well, how do you find the max of a function? You do the derivative of it and set it equal to 0. Well, if we want the max of A prime, we do the derivative of it, which would be a double prime, and set it equal to 0. Okay? That's one way to think about it. Another way to think about it is if you were to graph the a function and you want to know when it's increasing the most rapidly, let's say the a function does that, where is it increasing the most rapidly? Where is this graph increasing the most rapidly? Isn't that an inflection point? Yeah. Inflection point is where it's the steepest, right? Where its graph is the steepest. That's when it's increasing most rapidly. How do you find inflection point? Where the second derivative equals 0, right? So either way you think about it, you're going to do the second derivative and set it equal to 0. So you can think of it as a max problem. And remember back to the chart, where did inflection points happen? When a prime was at a max or a min, a local max or min. Remember that? When we go back and think about the chart, if we were looking at graphs, you want an inflection point of f, you could look at the maxes and mins of f prime. So you find that by doing when a double prime is 0. So you can use your calculator, although it's not very hard. A prime, they wrote it in a way that makes it actually pretty easy. The derivative of this, that would be go away. This would be just 48 times the derivative of that, which is 1. And then minus, and then this would be 12 t minus 3 to the second, derivative inside would just be 1. So that's a prime. A double prime, that would go away. You bring the 2 down in front, that'd be negative 24 t minus 3 to the first equals 0. When does that equal 0? When one of those is 0, which is just going to be that. Right? Isn't that going to be at t equals 3? Right? I mean, you could do it on your calculator, but they actually even wrote it in a way. A lot of times they do that in the no calculator to make the derivative pretty easy. You wouldn't have to distribute that or anything. You could just, your derivative is just pretty quick and easy, really. Okay? So when t equals 3. And now, here's the next part. Now, normally, showing that something is a max, we would need some sort of justification, right? If this was free response. Number line, list of candidates, something. Inflection point. How did we show something was an inflection point? We had to show it changed concavity. How did we do that? Number line, right? That's what we did. Remember we used to do F prime number lines to show local max and mins, and we did F double prime number lines to show inflection points, right? Well, that's also your justification, one of your justifications for a maximum, right? So if you had, now, I wouldn't do this if this was the actual test. I wouldn't spend time doing this. I would just, now, you might be a little nervous about, oh, I got this one candidate. What if it's a minimum? Well, if this is a minimum, then where's the max? There wouldn't be one, right? But one of your options is not, there is no max. You know what I mean? So when I look at this one, I get one candidate. There's got to be an answer. I'd feel pretty confident that it was C, right? Wasn't this one C? Okay, 3 hours later, so it started at 8. So we had 3, you're at 11. And so I'd feel pretty confident on that one. But if we wanted to do it, we could actually do a number line. So we could come over here, put in a 2, that'd be negative times negative is positive. And then put in a 4, that'd be positive times negative is negative. Sure enough, A double prime is positive, then negative, which means A prime is increasing, then decreasing. So A prime is a max. Or you could say that means A is concave up, and A is then concave down. So A changes concavity, so you have an inflection point, which is what we were looking for as well. So it's a really good problem to review those concepts about inflection points and chart, number line, and all that stuff. Okay? But again, in the beginning, you just can't set A prime equal to 0. Then you'd be finding the max amount of product being produced. Right? That's what what's the maximum number of items being produced at what time? But that's not what it asks. Okay? All right. 43. This is Shanghai. This is Shanghai. How many points on this curve? So you could go to your calculator and you could graph this thing, and I don't know what it looks like, whatever. 5th degree. Who knows? At how many points on this curve will the line tangent pass through the origin? So, right here would be a tangent line. Got sound effects and everything. Right there would be a tangent line on that curve that passes through 0, 0. Are there some other ones? Well, the way my picture looks, maybe not. But, you know, depending what the graph looks like, there could be some other ones, right? Why is this Shanghai? Well, no, that's how we do Shanghai. Why is this Shanghai? Why is this Shanghai? What is the Shanghai problem? Oh, come on. I thought we were ready to get into Shanghai. Macy?
No point on the tangent line, but not on the graph.
Yeah, you don't know the point where the tangent line touches, but you do know some other point on the tangent line. That's what Shanghai is. When you know you have a tangent line, it touches a curve somewhere, you don't know where, but you do have some extra information like where it touches somewhere else, right? Where it's at somewhere else. That's why Shanghai. So, Matilda, the way we do Shanghai is what? Two ways to find the slope. One is the slope between these 2 points. So y minus 0, x minus 0, right? And what is y? What can we put in place of y? This right here. So you're going now this is where the calculator really comes in handy. So everybody get your calculators out. Let's do this. So we got y over x. And then what's the other way to do slope? The derivative, y prime, which would be the derivative of this, which would be 20x to the 4th minus 12x to the 3rd plus 15x squared. No, what am I doing? 30x, I'm doing the derivative, right? And the 6 goes away. Do a solve on that on your calculator right there. Now, a little bit nervous because, you know, it may say, hey, warning, more solutions may exist, whatever. You know, the other thing you could do is you could graph this, and check how many intersections they have, because that's the same as solving an equation, basically. Where does this graph equal this graph? See where they cross. You do that. But I think we just do a solve. I think it works here. I think we come up with it. And what was the right answer?
1.
It was 1. Okay. So what should happen when you do a solve is you'll get 1x value. You'll get 1x value. Okay? If you'd got 2x values, then there'd have been 2 places where that happens. 3x values, there'd have been 3 places. Okay? Now, it's possible you could have graphed it. You know, again, it's a multiple choice question, so you don't have to show on the actual test. So it's possible you could have graphed this thing and just kind of did what I did here. You could have looked at it and said, you know, just kind of looked at all the tangent lines and looked to see how many looked like they might go through the origin. You know, I mean, if you're desperate, what the heck? Right? You got time. If you have time, you know.
That's what I did in the graph. It's just like it goes through the origin.
Like that, so it looks like that's.
So it just goes like that.
And the graph can't go through the origin, can it? It's got to go through 0 and 6, I think. If I put a 0 into here, I get 6 out for y. But it may, depending on your window, it may look like it's really close. I mean, it depends on your window.
Yeah, I must have typed it wrong because I
Oh, okay. Yeah. But I think you might, I mean, if you graph it and look, it might be fairly obvious that there'd only be one. Like on the one I have right here, it kind of looks like that'd be the only one. All these tangents go up here. These would all go, you know, way over here. You know, now it looks like that, you know, that looks like one and then all the rest. So my graph now up here looks like there'd be only one. But, you know, so maybe you can end up guessing, you know, when it comes to the actual test on something like that. But that's a Shanghai. Tangent to the curve at a point we don't know, but we do know some other point. All right. 44. A population grows according to, we have a few minutes here before to spend this. Population grows according to this. This is the number of people for time t that's positive. The population will approach a limiting value as time goes on. During which year, and that may or may not be important, during which year will the population reach half the limiting value? Oh, well, yeah, it's going to be pretty important because right now I need to know when this equation will equal half the limiting value. So I better find the limiting value. So, okay, limiting value would be what? As time goes on, that means t goes to infinity, right? So let's look at this as t goes to infinity. Well, I only have one t right here. So as t goes to infinity, this is going to be negative infinity. What's e to the negative infinity? I hope you guys are just shy because you should be shouting that out. What?
Very small number plus zero.
Yes. What's a negative power do? What's negative power? Reciprocal, flips it, right? What is that? Zero. Zero. Just being quiet like you. 0 times 5,500. 0. 6,000 minus 0. 6,000. The limit is 6,000. So it is a limit problem, isn't it? It really at its heart is a limit problem because from here on the rest is easy. We just use our calculators, right? So we're going to set this equal to 3,000. Half the limiting value. Now just let your calculator solve it. Right? Just let your calculator solve it at this point. Right? Half the limit. So it's really a limit problem. It's just as t goes to infinity, as this goes to infinity, what happens to that? It's negative infinity, which is 1 over e to the infinity. 1 over a really big number is just 0. And so that part is just going to kind of disappear. And this goes to 6,000. Yes? Well, yeah, okay. Well, let's talk about that. You're right, because look at the answer. So what'd you get? 3.8. Okay, so population grows according to this time where t is measured in years. So 0.5 would be during which year? When you're 0.5 years old, during which year of your life is that? That's the first year of your life. So even 0.2 would round up, right? So would you say it was 3.8? So what if that would have been, so that would be what year? The 4th year. What if it would have been 3.1? That's still the 4th year, right? 3.1 is after you, right? When you turn 18, the next day, you're in your 19th year, right? You're in your 19th year at that point, right? When you turn 18, well, actually, a second after your birth time, right? You're in your 19th year. Okay? So 3.1 would be in the 4th year, right? All right. So that's an interesting take on it. Okay? All right. Okay. Oh, how about 45? Let's. Oh shoot. Okay, forget 45. I wanted to talk about a free response. And, we can come back to it later. Okay? Here's what I want to talk. Now we'll have another chance this week. We can talk about. I want to talk about 2. Now 2 might be easier than some of the other ones, so you might be disappointed to talk about 2. But you know what? I want to make sure we can get the points on the easy ones, the ones we should get points on, right? And there's going to be some harder ones. Remember, 65% is an A. Let me keep reminding you that, right? 65% is an A. So there might be some that are just going to be hard, that you might miss those points. But you want to get as many of them, get the easy ones, okay? So here's a velocity of a particle moving along the x-axis. So you got something, you're just moving. It's like Bismarck, right? And just moving back and forth, right? East and west. So what is the position? Forget t equals a for a minute. How would you find position from velocity? Antiderivative. What would be a good name for the position of a particle on the x-axis? P would be not bad.
S.
S wouldn't be bad. What axis is it on? X would be better. My position function, I'm going to call it x of t. X is actually the output because at some time, that's my input, I'm going to have a position on the x-axis. So x is my output. So x would be better. Okay? So what's the antiderivative of 3t squared? We raise that up to a 3. We divide by 3. T cubed. What's the antiderivative of that? Raise that power up to a 2. Divide by 2. Or maybe you just figure it out in your head, right? You just figure out working backwards. Don't forget the plus c when you do an antiderivative. Now, we're not ready for this actually yet, but some people get all bent out of shape about the t equals a. Well, just pretend it said t equals 4. What would you do if it said determine the position of the particle at t equals 4? You'd plug in a 4. So plug in an a. That's all it means, right? Plug in an a. And we'll talk a lot about that over time. We get these problems that they have a k or an a or something in it, and people always, we panic sometimes. We don't, just do it the same way you do it if it was a number. Think, what if that was a 6? And then what would I do? And then do that, except then put the a and not the 6. Now, we're not ready for that though, because we need to put a c. We need to figure out what c is, and we have information right here. Right? So what would I do with this information? I'd put a 0 in here, and I would set that equal to -6, because that's the output. That's the position of the particle. So I put a 0 in for t. Well, 0, 0, so c is going to be -6. So my position function is, so x of t is t cubed minus 6t squared minus 6. So what's the position at a? You plug an a in. So it would be a cubed, let me write down here, a cubed minus 6a squared minus 6. That's the position of the particle with an a plugged in. Okay? Write expression for the speed of the particle. This might be the first one we've done this. I'm going to call that S. It is so easy. That's the easiest thing you'll ever do in this class right here. Is if they give you velocity and they want the speed, put bars around it. That's all you do. Speed is the absolute value of velocity. Speed is the absolute value of velocity. That's all you got to do. Okay? In which direction does a particle begin moving, and when does it turn around? So what would be a good thing to tell us about the direction? The velocity. And when does it turn around? What happens when it turns around? The velocity is 0. So 3t squared minus 12t. Now you got a lot of room to write this. I wouldn't be squeezing it in here like I have. Great, you got all that space in those different parts. 3t squared minus 12t equals 0. Factor out a 3t, you get t minus 4 equals 0. So at t equals 0 and at 4. Right? Now they told you that t is greater than or equal to 0. So when we do our number line, which isn't that what we would do next? We would do a v or an x prime number line here. Put a 0 on here, put a 4. We don't have to put in anything to the left of 0. Okay, we could, but it doesn't matter. But we could put in a 2, put in a 5. We're going to put that into our v, which I'm going to put it into this version here. So I put a 2 in there, that's positive. 2 minus 4 is negative. Put a 5 in there, that'd be positive, positive. So this particle starts, so what direction does it begin moving? Left. After 0, it goes left. And then when does it turn around? At 4. Right? And then your number line is there, and you can say, because the velocity is negative, and when does it turn around? That's when the velocity is 0. So, I didn't say justify your answer, so probably not a big deal. When, if ever, is the particle at the origin? What would you do for that? Take your position equation, which is this one. Set it equal to 0. At the origin is when the position would be 0. So you would take your position function, you would set it equal to 0, and then, is this a calculator one? I think it is, isn't it? I hope so. I don't know how, I'm not sure I don't think I could. We could solve it out, right? So use your calculator. So, but write it out. Set that equal to 0, solve it, and it'll tell you times. You get a negative time, ignore it. solve it and go. Okay, and I don't know, has anybody done that? What's it say? What was this, number 2? 6.158, I think is what it according to the book here. Yep, 6.158, solve it. Okay, so once, it will be at the origin one time at 6.158 time units, whatever those units are. All right, let's put those aside and for the time being, and let's talk about something that we need for today. It'd be a good idea to have your calculators handy. We're going to need those for sure. All right, and so today we are going to talk about something called Newton's method for finding zeros of a function. Newton's method for finding zeros of a function. Now, this is not something I ever learned when I was in school. This is something that was more important way back before any kind of calculators and those kind of things. If you actually had to do this. And now it's become more, and now we study it because we have these calculators that can do, because the calculations get just ridiculous. The multiplication and the number of digits, and it's just off. And so we never did it back in my day because it just wasn't worth all the effort, just as far as a learning process. If I was some scientist or something that had to work out some equation, that's what they did. I mean, that's people that had to do these hand calculations. It was just something they had to do. They had no other option. And so we never really studied it because you couldn't learn much from it if you couldn't go through the calculation. It just took too much time, wasn't worth it. But now that we can let the calculator do it, it's a neat thing to process to talk about. And we can understand how our calculators, when we do the solve, the magic button, right? When we do a solve, like on that last problem where we just let it solve it for us and gave us 6.158, how did it do that? How did it do t cubed? Matter of fact, we'll do a similar, let me see. We're going to do a similar problem to the one we just did. If I've got x cubed plus x plus 3 equals 0, and I want to solve that, how do we do it? If it's a quadratic, we got the quadratic formula. If it's linear, of course, that's really easy. But once you get to a cubic, we have no way of solving that. It doesn't factor, right? There's no way of knowing. Now, so back in the day, way back, when everything was done by hand, and Newton was one of the co-inventors of calculus, is it important in calculus to find the zeros of an equation? Absolutely. Without it, what could you do? I mean, you couldn't do any of the stuff we've done. Right? Even commented the other day when we were doing Luke Skywalker, how so many of you guys are so programmed right now to set equations equal to 0, right? It's so important. So how did they do it? How in the world did they do it? How did they find that? Okay? Yeah, I mean, that's kind of it, to be honest with you. How did they find this? Well, one option is, like you said, let's just start guessing. Right? Let's just start guessing. So let's say, and let's call this f. Let's just call this function f. Okay? So let's try f of 1. I don't know. Let's just try it. What do we get? 5. No, that's no good. Let's try 0. 3. We're getting closer. So what might be something good to try? How about negative 1? Let's try negative 1. Negative 1 plus negative 1 is negative 2 plus 3 is 1. Let's keep going. We're on a roll. We're getting close. Negative 7. Now we're getting farther away. Does that tell us anything right there?
Somewhere between -1 and -2.
Now, we're going to learn about a theorem here a little while later called the intermediate value theorem. The intermediate value theorem says when a function is continuous, which this is because it's a polynomial, if a function is continuous and it hits 1 and then it hits -7, somewhere in there it had to hit all those points in between, didn't it? The only way it could miss any of them is if it jumped. But if it's continuous, it can't jump, right? We talked about that. Can't be a gap. So if you've got a continuous function, which we have, and it hits a y value of 1, and then it hits a y value of -7, somewhere in there it had to hit all of them, which means somewhere it had to hit what? Somewhere it had to hit 0. So somewhere between -1 and -2, there is one. Now, there might be more than one, but we know there's one there. So that's what they would do. It's kind of a guess and check. Now, you guys might remember this. You did some synthetic division in Algebra 2, or was it with Mrs. Payne? I think it might have been Algebra 2. So, and you remember how to do it, but we did it. And it had to do with finding roots of polynomials. Now, the downside of that method was it only gave you, it only works for polynomials. And what it had to do with was the factors of this coefficient, the factors of this coefficient. You would try those and see those are possible places where the roots could happen, so you could try those, and then you would check in between, and if you knew, like we just did, if it changed from positive to negative, you knew there was one in there somewhere, and so you could guess, and you could keep guessing, and whatever. So that would be one option, but Newton and others, were like, there's got to be another way. I mean, it's kind of named for Newton, but I don't know that it's necessarily his method, or that he is the one that necessarily did the whole thing. So here's how Newton's method actually works then, and it actually uses the ideas of calculus. So let me show you, this isn't a graph of the one we're talking about, but it's similar. Okay, and this one happens across right here at 2. Okay, so we can see. I mean, if you have a graphing calculator, right? But that's the other thing. That's another thing they would do back in the day, is they would take something like this and they would graph it. But how would you graph it without a graphing calculator? If all you could do by hand, just plotting points is not a really great thing, right? So do the derivative, find the maxes, that kind of stuff, which you could do with this one because it's x cubed. But the problem with finding the maxes is if it was x to the 4th or x to the 5th, we did the derivative set equals 0, we might be in the same boat, right? We can't find where the derivative is 0 because we can't solve this equation because we got to do everything by hand, right? So again, it's the same dilemma. So here's how we would do it. But since we have a graph, we're going to go ahead and look at a graph. Again, this isn't the same graph. It's similar, but it's not the same graph. We're just going to understand the process, and then we're going to write it out and see where what it comes to. So what we're going to do is the same thing. We're going to guess. Okay? So we're going to make a guess. So we're going to say, let's say we think 3. 2.99. 2.02. Every time I let go. Okay, so we're gonna guess 3. Which is just what we were doing, right? So what did we do? We guessed. We started at 1, right? And what did we do with that? Back on this page, what did we do with our first guess? 1. Plugged it into the function. Now they could do that because all that involves is cubing and adding, right? Which is multiplying. So they could do that even if they were going to guess 2.7. They'd have to cube 2.7. So on their paper, they would write out 2.7 times 2.7 times 2.7. Aren't you glad you live now and not then, right? So you would write that out. But at least they could do it. It was doable. It wasn't a lot of fun, but it was doable. But they didn't know any different. They had to do it that way all the time. Okay? So they were all right. So we're going to do that. Okay? So we're going to plug it in. There it is. Okay? Now, here's what Newton's method says. Newton's method says that if my guess is pretty close, right? You know the thing we did with locally linear? We said that when we draw a tangent line to a curve, it touches at only one point. But if you look really close around that point, aren't the points on the line, aren't they pretty much the same as the points on the curve? You know what I mean? If I was to draw a tangent line, for example, I'm going to do that right here. I'm going to draw a tangent line. So the blue line touches this curve right at that one point. But right in this area around it, the points on the line are almost the same as the points on the curve, correct? All right. So here's what Newton's method says. Newton's method says that if I make a guess, and it's not 0, the y value is not 0, I'm going to draw a tangent line at that point, which is easy, because what do you need for a tangent line? What do you need to write a line equation? Point and a slope, right? To write any line, you need a point and a slope. Well, we already got the point, and the slope's easy, so we can just do the derivative and plug in that point, right? We don't have to solve the derivative, we just get the derivative, which is easy, and even back then without a calculator, it's easy. And then we can plug a number into that, which is easy, right? Might be some calculating, but we can do it. So we can get the point and the slope and rewrite the equation of that line. Now, if the point is pretty close to the root, won't the tangent line cross pretty close to where the graph crosses? Wouldn't it? Because if the points on the tangent line, if all these y values on the blue line are pretty much the same as on the black line, then the blue line and the black curve are going to cross at about the same point. So instead of figuring out where the black curve crosses, because we can't, we'll figure out where the line crosses. Now think about it. A line equation is this. A line equation is if we get the equation of the line, it's this, right? Can we see where that crosses the x-axis? Can't we always solve a line equation, linear? It's easy, right? Subtract b, divide. Think back 200 years ago. Easy. All they had to do was subtract and divide. They could do that. Again, it might be messy with a lot of decimals, but they could do it, right? So if it really was life or death and they needed to do this, they would do it, right? But it probably wasn't a lot of fun for a student to have to go through all those calculations, but whatever. And that's why when I was in school, we didn't do this, because it was all this dividing and adding of all these crazy decimals. At some point, it just wasn't worth all the effort it took. With our calculators, the calculator's going to do all that effort for us. Okay, now, is that going to cross exactly where we want it to? Probably not. So what do? We repeat the process. We solve that line equation, right? We take the mx plus b, set it equal to 0. We solve that, and that tells us where the line crosses the x-axis, and that's going to be our next guess. So what did we do with our first guess when we started? What did we do with our first guess, very first step? Plugged it into the function. So now this is our second guess. So we're going to repeat the process. We're going to plug it into the function. Do we get a 0? No. But are we getting closer? Yes. So we're going to repeat the process. We're going to draw a tangent line there. Look at the green tangent line. Right? Because now our points are getting closer to this root. So again, the points around the point of tangency, the points around that point are pretty close to being on the black curve. So where the green line crosses the x-axis is pretty close to where the black curve crosses the x-axis. And again, can we solve this line equation equals 0? Sure. Any linear equation is easier to solve. So what Newton, the genius of the method is, I can't solve a cubic equals 0. Let's turn it into something I can solve, which is a linear equation. And that's using the tangent line. And so find that x-intercept. Is that 0? It's pretty close. We repeat, go, and we get closer and closer and closer until we get as many decimal points as close as we need. Now, what happens? What are some bad things about Newton's method? What happens if you make a bad guess? You're going to be doing it for a while, okay? Because the tangent line crosses there, right? And then our next guess, and our tangent line crosses there. And then our next guess, or that is our next guess, and then our tangent line crosses there. But eventually, right, it's going to get closer and closer and closer. All right, now, let's change the function a little bit here. Okay. Let's see. I wonder if I change. Ooh, that's not good. Come on. Okay, I'll tell you what, let's just do this. So let's say I have a function here that goes like so, and I want to find this across a lot of different places. Okay? Well, let's say I pick this as my first guess. And it happens to be right at that peak. Where's the tangent line going to be? Where's that going to cross? Never. That'll be bad. Right? Here's another thing that can happen. Doesn't happen very often, but can happen. What if this is my first guess? I plug it in, I draw my tangent line, it crosses here. Then I plug it in, and I draw my tangent line, and it crosses there. And then I plug it in, draw my tangent line, it crosses there. And now it just keeps giving me those back and forth, right? Cycles back and forth between those 2 points. That's bad. Okay? So, if you plug in and have a kind of a real shallow, flat tangent line, it's going to shoot you way out here, right? And so, eventually, you may find it, but you may end up finding that root, not this one that you thought you were finding, that kind of thing, right? So there are some issues that can happen with Newton's method. But if your initial guess isn't bad, okay, so the idea I want you to take away from this is, what does Newton's method do? It's find the tangent, guess a place where it crosses the x-axis. First of all, it's finding where a curve crosses the x-axis. That's what Newton's method is for. Finding the root. How's it do it? You pick a point that you think might be close, you plug it into the function, you check, see if it is 0, it's usually not. Ride the tangent line down to the x-axis. Think of that term, riding the tangent line. You ride the tangent line down to the x-axis, use that guess and repeat. And eventually it'll zero in, no pun intended, on the root. It'll zero in where it crosses the x-axis. Now, how do we do that? We're going to start kind of by hand with a little bit of aid with our calculators, and then I'm going to show you kind of a super duper shortcut that you can do on your calculator. Okay? So let's do this problem right here. So the first thing I want to do is show you where Newton's formula comes from. Let's take what we've just talked about. And put it into some notation. So this wouldn't be a bad idea for you to write down. It'll be a one-time thing, though. What we end up with at the end is what you're going to have to be able to use. You're not going to have to memorize it. It's going to be on our take-home quiz that we do, that I give you later in the week. But you'll be able to use your notes and work with work with people, whatever. Okay, so here's the thing. So function is f. We're going to let x sub 0 be our first guess. Okay? So the first thing we do, right, is we plug that into the function, right? So we have our point, x sub 0, f of x sub 0, right? So remember, that's how we started. So we plug in our guess into the function, we get a point. Now we also need the slope at that point. What would be the slope at that point? What notation would we use for that? Not y prime, or maybe you said, but f prime, right? F prime at x sub 0, right? That would be the slope at that point. So now let's write the equation of the tangent line. So the equation of the tangent line would be y equals the slope, right? I mean, I'm just doing this. M x minus a plus b. That's all I'm doing right now, right? So what would I put in for the slope? F prime of x sub 0, parentheses. Then I'm going to put x minus, what do I put for the a? x sub 0 plus, what do I put for the b? F of x sub 0, right? So I got both of those things. I have my original guess, I have the y value I got when I plugged that in, and then I've got my slope, which is when I plug my x sub 0 into the derivative, right? Okay, and then what did I say I wanted to do with that? I wanted to set that equal to, I want to see where that line does what? I want to see where that line crosses the x-axis, which means I want to see when y is 0. So I want to put a 0 in there for that y, right? And I want to solve for what? I want to solve for x sub 0. I already know what x sub 0 is, right? That was my guess. I'm solving for x, right? I'm solving for that guy right there, right? I want to know where this line, I want to know at what x value this line crosses the x-axis. So I will solve for x. So how can I solve this for x? How can I get that out of there all by itself? What can I do? Let's pretend it said this. That's a little different. You'd probably say distribute that. I would say distribute that too, but I think that'd make this messier. What's another way we could start solving this? Subtract. Yeah, subtract 7, right? That's one thing I could do. I'm going to subtract f of x sub 0. So over here I got negative f of x sub 0 equals f prime x sub 0 times a quantity x minus x sub 0, right? Now what can I do? Divide by f prime. So I got negative f of x sub 0 over f prime of x sub 0 equals what? X minus x sub 0. Then what? Add x sub 0. Now when I add x sub 0, I'm going to put it over here to the left of this. So I'm going to end up with x sub 0. I'm going to go to a new slide here in a minute. Minus, and then this fraction, f of x sub 0 over f prime of x sub 0. And that would equal my x. And then what did we call that x? What were we going to do with that x we just found? What's that? That'll be my next guess, and I'll just repeat with that, right? So what can I call that? How about I call that x1? That would basically be what I just found is x1. And then I would repeat all of this, right? Well, we don't want to actually do that with, I mean, one way would be to do that with actual numbers, right? Like we put in a 1 as our first guess, right? So I got the 0.15, so I could have put a 1 there and a 5 there, and I could have done the derivative of this, put a 1 in and found that. I could have solved and found this x, and then I could have repeated. And I could have kept doing that over and over and over again, right? But what I've done here, by doing it this way, is I found myself a formula for how to find that next guess. And that's what Newton's method formula is. So we're going to write it out here. So my next guess, I'm going to call it xn plus 1. So my next guess is my previous guess minus f of x over f prime of x, and that is the formula for Newton's method. But it comes from, don't ever forget, with Newton's method, because on the takeoff test you might be asked questions about this to describe this and that kind of thing. Where did this come from? It comes from a line equation set equal to 0. That's where it comes from. This line right here. It's a line equation set equal to 0. It's the tangent line equation set equal to 0. So it came from, this little formula comes from where does the tangent line cross the x-axis. That's what it came from. So when we're doing this thing here, the key to this is your first guess. Whoops, move that over. Key to this is your first guess. Find where that tangent line crosses the x-axis. That's the key. First guess, tangent line, where does it cross the x-axis? Repeat. Point, tangent line, where does it cross the x-axis? Point, tangent line, where does it cross the x-axis? That's what we're finding. And where it crosses the x-axis is getting closer and closer to where the actual graph crosses the x-axis, which is what we want. We want the root of that curve, which is where it crosses the x-axis. So, how can we use this formula? So let's do it with the problem we were just doing. We're going to do it with a table. This is the, well, it's a shortcut compared to Newton's day, because you guys have calculators. But it's not as short as we're going to make it here in a minute. All right, so here we go. So we're going to write down f of x. It was x cubed plus x, what was it, minus 3 or plus 3? Plus 3? Okay. I'm going to do the derivative of that because we're going to need it. So that would be 3x squared plus 1. Okay. All right. So I'm going to make myself a table here. So in this table, we're going to have an x column. We're going to have an f of x column. We're going to have an f prime column. On your take-home quiz, you're going to have, I think, I don't know if there'll be a Newton's method on the take-home, but on your homework there will be. And you're going to do it with a table here. Okay? And then there's going to be an f over f prime column. And then finally there's going to be an x minus f of x over f prime of x, which is the actual formula. Okay? And now we're going to get to use our calculator. So let's start with 1 as our first guess. Now we know it's somewhere between -1 and -2, but let's start with 1 as our first guess. So we plug that into our original, and we already did that, and it was what? 5. Now, go on to the next column. We're going to plug that into we're going to plug that 1 into our f prime. What do you get for that? 4. Okay? Now what do we get when we take f divided by f prime? 1.25. Yeah, let's use decimals. Fractions will get kind of crazy here. So on your calculators, now we'll use our calculators here, well, in a minute. 1, so now this column is x column minus that column. So 1 minus 1.25? -0.25. And what is that number? That is my next guess. Now, this will shorten your work a little bit. Everybody on your home screen, on your calculator screen, let's define this. Let's define this as f, and let's define f prime as g. That'll just make things faster. So go on your calculator screen, go define. You can just type out the word define, or it's in your menu under 1, under actions or something, I think. Define f of x to be this, x cubed plus x plus 3. And define g of x to be the derivative. It'll just make things go faster here. Okay? Right? Yeah, I think you have to use the word define to make this happen. Okay? So this is where we got a big advantage over Newton's day, right? Because now they would have to put -0.25 in here and cube it. But they could, but it would just be a pain. Plus -2.5 plus 3. Wait till you get one that's like 9 decimals long, right? Really would be a pain to do by hand. But it's doable. Whereas finding the root of this is not doable any other way. Okay? All right, got it? So for this column, we're going to do f of -0.25. What do you get? Rachel, what do you got? Did you do it? Oh, I don't care. Whoever's got it first. Let's do f of 2.734. Now, you might want to hang on to that number. You know, that number's out there. You can grab it later. We don't have to put all the digits in. We'll just put like 3, but then we'll go up and grab it here in a minute. Now, let's do f prime, which would be your g function. Do g of -0.25. 1.188 or whatever. Okay, but you got it on your calculator. Now we got to take the f divided by the f prime. So go up and grab this number divided by that number. Right? And it'd be good to grab the ones that are not rounded. So the f number divided by the f prime number, what do you got? Two point what? 30. Why does this not seem right?
That's what I got.
Okay, all right. And then we're going to do x minus that. So this minus that.
It's 2.303.
That's fine. That's fine. But because we're using, in our calculators, we're using the unrounded one. So let's do this minus that one, and it'd be and again, use your unrounded one from your calculator. What do we get? Negative 2 point what? 553. Gosh, what? Okay, all right. Negative 2.553. Didn't we say we were going to get one between -1 and -2? It was going to be closer to -1. Okay, I'm a little sprayed. Okay, quickly, let's do f of this one now. F parentheses, then go up and grab this one. How much?
Negative 16.18.
Okay. Point what? 185, okay, fine. And then g, or the derivative. What are we getting here, anybody?
20.548.
Okay. And then we're going to take the f column divided by the f prime column. Negative point, okay, that's better. Negative 0.8. 788.
No.
And
No first aid.
no first aid.
Yeah.
Negative 0.788.
788.
And then it's x minus that. Okay, this is getting better. So -2, that number, which arrow up and find that number, minus that number. Okay, that's better. We thought it was going to be between -1 and -2, right? And probably closer to -1, right? Because -1 gave us 1 and -2 gave us -7, right? And we're trying to get 0. So we think this number should be getting closer to -1, okay? So let's go one more time. We got enough time to do one more row, and then you're going to finish this as part of your homework. Okay, so let's do f of this number. And somebody else, you guys over there do g. You guys, Caleb, you Reed, whatever, you guys do g of that number. We'll speed it up here. Somebody over here do f.
-4.263.
-4.623. Now, isn't this the column we're hoping gets close to 0? But isn't this the column we're hoping gets close to 0? Right? This column here? Because, right, we're taking this x and we're plugging it into f. We're looking for the root. So eventually this one better start getting close to 0. Okay? All right, so what was the g one? What was the f prime? 7.10. I'm sorry.
What is that f that said?
4.263. 263. And this one says 10.345. Now we're going to divide those. So f divided by f prime. Point what? 412. Okay. And then this minus that. 353. Okay, which becomes our next guess. All right, now it's going to start getting closer here. Now I'm going to stop right there. I just want to explain a couple things. There's two really important columns here to pay attention to. This column and this column should both be getting closer to 0. This column should be getting close to 0 because that's the whole point. We're trying to find the root. We're trying to find where the f function is 0. Why should this column be getting closer to 0? Well, okay, good point. Yeah, if the top is 0, then because this was getting close to 0, then this is. But I guess what I was getting at is, isn't this column the difference between our previous guess and our new guess? Right? Because we take our previous guess and we subtract this column. So as we start getting closer and closer, we should see what? What should happen to the numbers here? No, not smaller. These are getting 0. These are going towards 0. What should be happening in this column? Evening. It should be coming the same number, right? In other words, at some point we'll get negative 1.127, and then we'll get negative 1.123, and then we'll get, you know what I mean? Because what's happening is this number here is where that tangent line is crossing. And it's getting closer and closer to the actual root. And so what's happening is, so you may have to go about 4 more times. I don't know, let's try to get until the third decimal place doesn't change. Keep going until the third decimal place there doesn't change. Now tomorrow I'm going to show you how we can really use our calculators for a super duper shortcut. But for right now I want you to write out this table. Okay, so your assignment, finish that. You might have to go about 4 more rows. You know, that took us 10 minutes, so that's not very much. Okay, probably I'm guessing about 4 more rows ought to do it. Might not even take that many. Might take a few more, I don't know. And then get going in sample 2. Okay? Get going in sample 2. Now, we will have some more time in sample 2. Part of your homework tomorrow will be in sample 2. But I think you want to get a pretty good chunk, that first multiple choice section maybe, or whatever. Okay? Because each day this week we're going to be doing a little bit of stuff. I think by Thursday or so we want to be pretty much done with sample 2, but we'll be doing a little bit in the book. Let me give you the take-home. So over the weekend it's mostly take-home work. Friday's going to be pretty much a work day this week. Okay? Probably give you the third packet, so you can be starting on that too, but you can be working on the take-home as well a little bit. Okay? So mostly tonight, sample 2. Be getting going in that. Okay, but finish this first.
Yeah, we have this today.
Can I go grab a reptiles?
What's that?
Can I go grab some?
What happened?
Stuff.
Spilled or
Yeah, I went to go get up and I knocked over.
Good bathroom. Good bathroom. Oh, oops, 3. Is that 3? Yeah, that's true.
Let me just show you my homework. Okay.
Oh, yeah. And that was the other Anton.
Yeah, the last one for finance.
Okay. Good. I'll have to look up and see if I even took points that day. I'm not sure.
When are we supposed to be